name is Kim Yoo-ji, and a third-year joint MS and PhD student. Today I will present Text2Room, extracting textured 3D meshes from 2D text-to-image models. It includes the well-known or familiar authors, and this is the oral paper of ICCB 2023. The content is as follows. There are several challenges in generating 3D models. First, one of the most prominent issues is lack of 3D training data. While relatively large-scale 3D datasets have been made available in recent times, they still get left behind in terms of scale and diversity compared to the large-scale 2D datasets. To address these challenges, there are some trials to lift the expressive power of 2D text-to-image models as 3D generation. There are representative work that utilize text-to-image generative models from 3D content generation. However, they cannot easily be extended to create room-scale or large-scale 3D structures and textures. In other words, recent text-to-3D generation task has been focused on object generation. To create room-scale 3D structure and texture, the generated output needs to be dense and coherent across outward-facing viewpoint. And output needs to contain all of the required structures of the room, like walls, floors, and furnitures. Adapting previous object-centric methods directly to generate room-scale 3D generation is challenging. Finally, mesh representation is still desired in many end-user tasks. Magic 3D is one of the prominent research in 3D content generation using text-to-image generative model. If we want to get mesh in Magic 3D, an additional convergence step is required to transform from the implicit representation NURB to the explicit representation mesh. So Text2Room proposes a method to address the previous challenges, which generate room-scale textured 3D meshes solely based on text prompt input. What's impressive point is its ability to generate complete 3D rooms, including the ceiling and floor. Text2Room addresses the aforementioned challenges through the following method. First, to overcome the lack of available 3D training data, they lift the 2D text-to-image model into 3D. Next, to address the difficulty of extending object-centric text-to-3D approaches to room-scale 3D generation, the following methods are proposed, and this method will be explained in the subsequent slide. Finally, method will be explained in the finally, to obtain mesh output, Text2Room directly optimize meshes using PyTorch 3D and classical rasterization function. So let's explain about the method. Text2Room separates the scene generation process into two stages. The first is scene generation stage, and the next is the scene completion stage. These two stages also adapt different viewpoint selection. And each stage goes through the following 3 steps, and I will explain them in detail step by step. The first stage is scene generation stage. In this stage, we sample the new camera pose, noted as green, and iteratively generate the whole 3D scene, but not complete. So this is the whole process pipeline. The result of rendered image and meshes show highly detailed generation quality. Next is the scene completion stage. This stage aims to fill the hole from before stage with a newly sampled camera, denoted as LED. This viewpoint selection algorithm is different from the previous stage, and their objective is complete the scene by sampling additional poses, especially looking at the horse and playing the horse. Before diving into specific details, I would like to organize the notation. The 3D mesh consists of vertices, vertex colors, and bases. Each mesh vertices also have a color. And this N0 notation means the union of natural number and zero. The input text and pose are defined at each step T. So there is the scene that is defined at previous viewpoint T-1. And we want to generate the 3D scene, so we change the viewpoint and fill this region. R is the rasterization function, and rasterization renders the image and depth map with the mesh and the sampled viewpoint as input. Because we change the viewpoint, the rendered image is not fully complete. And MT means the image space mask. So there is a binary mask for splitting these two images. By passing the rendered images, this and mask and text prompt through the text-to-image inpainting module, we can obtain an inpainted image like this. In this case, the text-to-image inpainting module is the frozen stable diffusion. Using the inpainted image obtained earlier, this, and partially rendered depths, we can obtain an inpainted depth map through the mono depth inpainting module. With the inpainted image and the inpainted depth map, the process is ongoing to lift from 2D into 3D through the mesh filter and fusion stage. And each stage, detail of these stages are on the next slide. So first is the depth alignment step, this one. In the monocular depth estimation, depth is an inconsistent scale with different viewpoint. If we directly use predicted depth for back projection from 2D to 3D, it leads to hard curves and discontinuity in 3D like that. So we need depth alignment step. So the goal we aim to achieve through depth alignment is as follows. We want to correctly combine the old depth and new depth content. And similar reason in the scene like walls or furniture should be placed at similar depths. So we need two depth alignment steps. In this paper, the notation is present as follows. The input is the rendered image and rendered depth. They are incomplete form. And with these two inputs, they conduct monocular depth in painting. However, I think it should be modified as follows. Not this rendered image, but the inpainted image. And with the rendered depth and inpainted image are taken as input to the mono depth inpainting module to obtain the inpainted depth. Although the alignment was proceeded in previous step, but additional optimization is performed to enhance the result further. In this equation, we optimize the scale and shift parameter between predicted and rendered disparity map. We mask out unobserved pixels via image space mask M. So when we optimize the scale and shift parameter, disparity is used instead of depth. Disparity has an inverse proportional relationship with depth, and I think it seems that disparity is used due to potential scale-related issue. And because this is the disparity, the aligned depth is like this, inverse. Finally, we smooth and align depth by applying additional Gaussian corner at the mask edge. Mask edge is here. This helps elevate seams that appear at the edge of the mask. So next is the mesh fusion step. Now we have inpainted image and inpainted depth map here. These previous stages involve generating a continuous scene image in 2D. So now we need to lift 2D into 3D. So this is the mesh fusion step. First, backproject the image space pixels into the world space point cloud. And use a simple triangulation scheme. This pipeline is based on my understanding of triangulation. Triangulation involves selecting 4 adjacent pixels in generated image to create 2 triangles, like this. Then project the pixel in 2D into a vertex into 3D, and the triangle in 2D into a massive base in 3D. It is small, but it is same formation. So it is an illustration of pixel triangulation. This naive approach with only pixel triangulation creates stretched out 3D geometry as follows. So we need 2 filters that remove these stretched out faces. The first filter is based on the edge length, and the next filter is based on the angle between surface nova and viewing direction. In figure B, red means the filtered face. After undergoing face filtering, we fused together the newly generated mesh patches, denoted as green, and the existing geometry, denoted as blue. We continue the triangulation scheme at all edges of mask. The proposed final method is camera pose or viewpoint selection for each 2 stages, plus choice of text prompt. First, regarding the text prompt, we need to discourage the text-to-image generator from generating furniture in unwanted regions. For example, at poses looking at the floor or ceiling, the text prompt will only contain the word floor or ceiling and without furniture. Regarding the camera pose, we first render predefined trajectory in different directions that eventually cover the whole room in the scene generation stage. It ensures the optimal observation distance for each pose. There are some details here, and in summary, we uniformly sample the camera position to cover the entire scene with a carefully rejection design like this. In the scene completion stage, the objective of viewpoint selection is filling holes, this area. It is impossible to choose sufficient poses a priori, so we can compute the scene by sampling additional poses posteriori, which are looking at holes. There are some details here, and in summary, we densely sample the camera position to cover the unobserved pixel. this LED camera. So, and with the newly chosen camera in the LED camera, we can render the image as shown in B and C. B is the mask and C is the inpainted result. Because text-to-image generator can generate better results for largely connected regions. So, two small holes like this are inappropriate to get reasonable inpainting result. To mitigate this issue, we first inpaint the small holes with a classical inpainting method and dilated the remaining holes in figure D. It makes mask larger, and text-to-image generator can generate better inpainting result with large connected regions. And finally, run Poisson surface reconstruction on the scene mesh, and it closes any remaining holes after completion and smooths out discontinuities. Through these previous steps, we can get the result, which is the watertight mesh of the generated scene. And it can be rendered with a classical rasterization function. Next is the experiment. So there are some baseline work to compare. First one is the generating object, and the second one is the method for generating enlarged viewpoint image with text-to-image model. And third one is method for generating RGB panoramas. And final one is method for generating more expressive RGB panoramas. So as shown in the table, Text2Room creates scene with the highest quality in quantitative result. And in the qualitative results, pure clean nerve cannot produce immersive scene with blurs and words. They only can generate the object. And outpainting does not produce 3D consistent scene. And text-to-light and blockade the big panorama method have holes due to occlusion. But in contrast, we create complete meshes without holes and higher details. So, in the ablation study, first one is the without depth alignment stage. Without depth alignment stages, scenes are disconnected and show many things. And without edge and surface normal threshold, many faces are stretched out. And without completion stage, the mesh has many holes. So with all these modules, Text2Room can create complete high-resolution scenes. And they can also generate the floor and ceiling, but for visualization, they remove this. And additional scene generation results are as follows. The first one is partial bearing scene generation, and the next one is scene generation with layout guidance. Both of them are for controllable way. And first one is create room with multiple parts by prompt mixing. And the second one is can generate object to be generated differently using different prompt and sampled viewpoint, shown in the diagram. And this is the conclusion. The limitation discussed in the paper are as follows. First one is the thresholding scheme may not detect all stretched out regions, and some holes may still not be completed. And final one is scene representation does not decompose material from lighting. It means that baked shadow or bright. It has baked shadow and bright. The additional limitation with my opinion are as follows. It is limited in single room reconstruction, so with many room reconstruction, they cannot. And it cannot reconstruct full objects. It means that occlusion is not reflected. However, the current results are highly promising, I think. So let's summarize the paper as follows. The overall goal is to generate textured 3D mesh from only text input alone. The key idea can be summarized as follows. First is the tailored viewpoint selection, and second one is alignment stage which makes the 3D mesh. And finally, the final one is the exciting application of large-scale 3D. I think it is crucial to appropriately design algorithm for correct viewpoint selection and iteratively fusion method, especially when generating large-scale or C-scan 3D. It's the final section of my presentation. And in the discussion section, I would like to introduce one more recent study that is similar to Text2Room. Recently, there has been a study called Lucid Dreamer that focused on scene-scale 3D generation using 3D Gaussian splicing 3DGS representation. While existing 3D generation methods have shown bias toward the training data domain rather than the input domain, so this method overcomes this challenge and called domain-free generation. It means that it can produce results that reflect the input domain, not training data domain. And they support different input types like text and RGB and RGBD.
I have a question that what does domain stands for? It stands for the training and test set. 도메인이 여기서 의미하는 게 어떤 거지?
그러니까 보통 뭔가 이런 제너레이션 태스크를 할 때 3D 데이터 같은 걸로 학습을 많이 하면은 걔를 이제 인퍼런스를 하려고 새로운 이미지로 인퍼런스를 했는데 사실은 트레이닝 데이터에 바이어스 되는 결과가 나오지 이 인풋 도메인을 반영하는 결과가 나오는 게 아닌데 본인 여기서 제안한 방법은 인풋 도메인을 잘 반영을 한다라고 주장을 하고 있습니다. 근데 사실 스테이블 디퓨전을 쓰기 때문에 스테이블 디퓨전이 되게 제너럴한 데이터로 학습이 돼서 그냥 그 모듈이 가지고 있는 성질이라고 저는 생각을 하긴 하는데 이제 본인들의 컨트리뷰션이라고 적기는 했습니다.
그러니까 인풋 도메인의 텍스트 프롬프트를 잘 어웨어한 결과가 나온다는 그런
아마 이미지에서 말하는 것 같아요. 텍스트보다는
이미지 인풋을 넣었어요.
네네.
네, 이해했습니다.
네. 네. So this is the result of the Lucid Dreamer. And in my opinion, it seems that 3DGS is well suited for larger scale application, especially in mitigating the hole filling problem through the optimization of 3DGS with point cloud initialization. But although there are many follow-up studies on 3DGS these days, it is essential to explore and understand its method and ability for scene-scale use, I think. So this is the end of my presentation.